Hello everyone. I'm going to try and make a quick video for you guys specifically talking about, we call this the 5% rule or 5% guideline for cumbersome calculations. This is kind of a topic in section 4.2. So cumbersome, if you think about that word, cumbersome means tedious. It means, I like to say, it's kind of a pain in the butt, right? If calculations are obnoxious to do, this is a rule for a shortcut where the shortcut saves us time in our calculations. So it says when sampling without replacement and the sample size is no more than 5% of the size of the population, treat the selections as being independent, even though they're actually dependent. So if we're doing this without replacement, that means whatever selection we make, we're making our selection, we're keeping that item out of the pool of options, and then when we make our second selection has been affected by whatever we selected in the first selection because we didn't put it back. We did it without replacing it. So normally that would mean that we have to write each fraction out, and each fraction would go down by 1 because we are taking one selection out of the options, so our fraction would go down by 1. But if you're doing this in what they would call a cumbersome calculation, that can be a lot of fractions. Like what if we're selecting, 8 or 10 items? We'd have 8 or 10 different fractions. So let's look at an example and we'll kind of talk about, we'll talk about what makes it cumbersome and how this shortcut helps. So our example says airport baggage scales can show that bags are overweight and high additional fees can be imposed. The New York City Department of Consumer Affairs checked all 810 scales at JFK and LaGuardia, those are airports, and 102 scales were found to be defective and ordered out of use. So it says if 2 of the 810 scales are randomly selected with replacement, meaning we select one, we put it back, and then we select again, find the probability that they are both defective. Okay, both defective. So this is for part A. I'll probably put it up here. The probability that they are both defective. Okay, so for them to both be defective, that means the first one is defective. The first pick is defective. I'm going to abbreviate that. And my dogs are making noise, of course they are. And the second selection is defective. Okay, so the first is defective and the second one is defective. So if it's the first one's defective and the second one's defective and tells me to multiply. Okay, so I know I am multiplying here. So for the first one, I'm selecting one scale out of the 810 scales, and I want to know the probability that the first one's defective. So it told us there were 102 defective scales out of 810 scales. Now this first time we're doing this with replacement, which means when I select that first scale, I make my selection and then I put it back into the list. I put it back into the pile so it could be selected a second time. So when I go to pick the second scale, make the second selection, there are still 102 defective scales out of 810 scales total, because I did this with replacement. So this isn't cumbersome at all. I could just type this in and I could be like, okay, it's 102 out of 810 squared, and I type that in my calculator and I get an answer. Okay, so if you type that in your calculator, you should get 0.0159 if you round it. Okay, so this is an example showing you something that's not cumbersome, it's not an issue, and since it was with replacement, it made it easier because our fractions stayed the same the whole time. So now let's look at part B. Part B says if 2 out of the 810 scales are randomly selected without replacement, find the probability that they are both defective. So we are doing the same thing but without replacement. Okay, so it is the same setup. And it's going to be doing 2 fractions again because we're making 2 selections. When I make that first selection and I want it to be defective, it's still 102 defective scales out of 810 scales total, times, for my second scale, my second selection this time, I didn't replace the first selection, which means like if I have a list of these 810 scales and I pick one out of the list, now there's 809 scales in the list. So the number in the list has changed because I took one out. So now there's only 809 scales in the list. Not only that, I took out a defective scale and I'm looking to pick another defective scale. So my number of defective scales went down by 1 as well. So you can see this one, the fraction changed each time. And so we would have to type these into our calculator and multiply them. Okay, so I typed that in my calculator and I got 0.0157. And so if you notice, this is actually very close to what we got when we did it without replacement. So part of the idea here is understanding that with replacement and without replacement, come up with very similar answers, depending on the problem. So that's one thing to kind of note. The other thing is, since we only had to do this for 2 fractions, right, 2 selections, it wasn't that bad to type it in the calculator, right? You're only typing it in 2 fractions. That's all right. That's not super cumbersome. But look at this next example. You're selecting 5 scales, which means you're going to have 5 fractions. And not only that, our numbers are a lot bigger now. So imagine having to type this in. For part C, we're talking about selecting 5 and that all 5 are defective. So all 5 defective. Okay, and our numbers would say, okay, we've got 1,259 defective out of 10,000. Okay, and then we're still doing this without replacement. So our next fraction would go down by 1, not replacement. It'd be 1,258 out of 9,999. Is that right? Yes. And then it goes down again, 1,257 out of 9,998. And you see how this would be cumbersome. This is what they're calling cumbersome. Having to do 5 of these fractions, having to change them each time, it's a lot. It's a pain in the butt. And we already figured out kind of up here that with replacement and without replacement ended up with similar answers. Okay, do you see that? They ended up really close. And so what this rule is saying is as long as your sample size is no more than 5% of the population, you can do your calculation like it's with replacement, even when it says without replacement. So let's confirm, let's check first that our sample size is not more than 5% of the population size. So in part C, our sample size N is 5. We're sampling 5 scales. Our population size, which we use a capital N, is 10,000. So that's definitely 5 is less than 5% of 10,000. That's a definitely. What we're looking for is a very small population, or sorry, a small sample to a very large population. So we have that. So it meets this requirement. And so because it meets this requirement, we're allowed to shortcut. Instead of doing all of this, we're just going to do it with replacement. And the key help, sorry, my dog's making noise again. Sorry. Okay. The key idea, the reason why with replacement helps is this. We can use one fraction repeated and use exponents to type it in our calculator. So we would do 1259 over 10,000. And we would do it to the fifth because we're making 5 selections. And what you'll find is this answer that we get is close enough, because we saw how similar these were. This answer is close enough that it's relatively accurate. And we used this shortcut, which saved us from having to type all these numbers in. Okay, so I'm going to type this in the calculator, and I'm going to go ahead and type this one in the calculator, and we're going to see how close it is. Okay, so just to compare, if you're doing this kind of the long way, right, which the long way I will say is technically the more accurate way, right? This is the way it should be done because it is without replacement. So this is technically the more accurate way, where you use a separate fraction for each selection. Since it's without replacement, your fractions go down by 1, and you would have a total of 5 fractions because we made 5 selections, okay? And so the answer for the probability that all 5 are defective is 0.0000314. That's from typing in all 5 fractions and multiplying them. With the shortcut, okay, this is the shortcut over here, I got 0.0000316. So technically, not 100% accurate. But look at how close it is, right? We go through, 6 decimal places before it's a little bit off, right? So the idea is this shortcut saves us time, makes things easier, and we only have to give up a tiny bit of accuracy, right? Because decimals that far out, we're not talking a huge difference here. So the idea is as long as your sample size is smaller than 5% of the population size, we can use this shortcut and we only have to give up a little bit of accuracy. And the amount of time that this saves for us makes it worth it. Okay? You're only going to want to use this for cumbersome calculations, which means like part B, they only had you doing 2 fractions anyway. They wouldn't consider that cumbersome, right? Because it's just 2 fractions. So you use it for things where you have large numbers that you're dealing with and you have lots of selections, right? That's what they're going to consider cumbersome. Okay, so I just wanted to go through this and kind of explain this concept. If you have any questions, let me know.